Alrighty, hi everyone, thanks for the introduction, Sam. I'm excited to talk to you about some work that I've been doing with my collaborators on a new version of CAF. I'll note that this is building on prior work on CAF, which is a cost-aware logical framework, but I won't assume any prior knowledge on that, so I'll just give you an overview of the full story. So first off, some motivation. You're all familiar, I'm sure, with the list map function, but when you think about cost analysis, you might realize that this is tougher for map than it might originally seem, because map is a higher order function, and the argument f might perform effects, so it's not immediately obvious how you would analyze map. So Decalf, which is a type theory embedded in Agda, will give us an elegant and linguistic answer to this problem. So first, let me tell you about the core language. There are three essential components. The first one is the use of effects. The second, which is new in Decalf, is this notion of judgmental program inequality. And then finally, we have a phase distinction, which is inherited from CAF, and we extend it to interact with the program inequality here. So first off, CAF builds on call by push value. So we split up our type theory into value types and computation types. Computation types are interesting because they let you perform effects at those types. F of A, just for notation, means that you're computing a value of type A, but you might perform some effects to do it. And the nice thing is, the computation types on the right let you incur effects, and they also retain some nice reasoning principles that we'll use to prove properties. So we add an effect called step to the C, which means that you should incur C units of abstract cost. So when we write step to the C of E, that means incur C units of abstract cost and then run program E afterwards. Here C is an element of some monoid, like the natural numbers. And there are these expected laws saying that, for example, if you incur 0 cost, then you might as well not bother. And if you incur C1 cost followed by C2 cost, you can consolidate those using the monoid structure. So in CAF, we had a notion of exact cost bound. And the idea is that to show a cost bound, you use program equality. So if you want to show that a program E of type f of A has cost C, you show that there's a value A such that E is equivalent to the program that incurs C units of abstract cost and then returns the value A. So for example, in merge sort, you know that for all lists L, merge sort of L has cost length of L log length of L, informally n log n. So in Decalf, we add a new notion, which is program inequality. E is less than or equal to E prime, where both E and E prime are computations of type X here. And the intuition is that E and E prime compute the same result, but E might be cheaper at doing it. So for example, the program on the left is less than or equal to the program on the right, because they both return the same result, but the left one costs 3 and the right one costs 12. So here, inequality is verifying cost and behavior simultaneously, which we'll find important in a little bit. And this is also inspired by directed type theory. This is a similar notion of inequality, just to note. So, similar to the slide before, we can now talk about inexact cost bounds using inequality, where we say that program E is bounded by a cost C when there exists a value A such that the program E as an entire program is less than or equal to the cost bound program that incurs C cost and then returns the value A. So now, for example, we can bound something like insertion sort. Insertion sort doesn't always incur the same amount of cost. It's cheap on a sorted list, but very expensive on a reverse sorted list. But in any case, the cost is always bounded by length of L squared. So just to compare equality and inequality, they're actually quite similar. They're both reflexive and transitive. Equality is interesting because it's symmetric, whereas inequality, of course, isn't. They're both, well, equality is a congruence and inequality is a monotone, different terminology for similar ideas, and they're both pointwise on functions. So since we have these nice reasoning principles, we can now compositionally analyze program cost using inequality reasoning. So I mentioned our type theory is embedded in Agda. This means that we can write some code in call by push value and prove properties about it. So using the insertion sort example, here's the auxiliary function insert written in call by push value, where we track 1 unit of cost per comparison. And we can prove the theorem that this insert function is less than or equal to the function on the right that just takes in an element, takes in a list, and incurs length of that list cost before returning some specification level sorted list. In order to prove this, we can just use a chain of inequality reasoning. So I'll show you an example case of the proof. To show this theorem, you would start with the code from insert on the left, and you would use, for in this example, monotonicity and the inductive hypothesis to simplify the code, and then some other properties about equality will get you to the desired form. So now I need to tell you about the third key component, which is this phase distinction, inspired by work by Sterling and Harper. So the extensional phase is a proposition that we have in Decalf, which isolates the behavior of a program. If this proposition X holds, then two things happen. First off, you know the cost model is trivial, and second of all, you know that inequality implies equality. And we have a modality open of A, that's just the function space out of the extensional proposition, that isolates the behavioral part of a type A. So as a corollary, we have this, this theorem called non-interference that says if you have a type that whose behavioral part is trivial, then every function out of that type into open of B, into the behavioral part of into the behavioral part of B is a constant function. The punchy way to say that is cost does not impact behavior. There are some other corollaries. So for example, if the extensional phase holds, you know the cost model is trivial, so every cost is actually just equal to 0, since you know you have a monoid. And therefore, incurring C cost is the same thing as incurring 0 cost, is the same thing as not incurring any cost at all. And using this kind of reasoning, we can prove good theorems about the behavior of programs, such as, well, as long as you're willing to discount cost, insertion sort and merge sort are actually just the same thing. So now let me tell you about effects, which we add in Decalf. So Decalf supports a variety of algebraic effects. In the paper, we have a bunch of examples, but for the purpose of this talk, I'm going to focus on probabilistic choice. So to add a probabilistic choice effect, we add a primitive just like step. Here we call it flip, which is like a weighted coin flip with probability p that you land in one branch and 1 minus p that you land in the other. This is pretty standard. Using this primitive, we can then define randomized algorithms. So for example, we can define the randomized parallel quicksort algorithm, which takes a list and returns an f of list. And remember, f means that you can incur some effects. So in the process of sorting, it's going to flip some coins and incur some cost. This is, by the way, benign randomization, so it's only for the purpose of getting a good cost bound, but the same value is always returned. Therefore, we can specify the given bound, which is a worst case upper bound for quicksort, saying that quicksort, regardless of how the randomization shakes out, will take in a list L and incur at most length of L squared cost before returning the specification level sorted list. And this proof is just by induction. As a corollary, we can use the extensional phase to notice that quicksort behaviorally is just taking in a list and returning the sorted specification, the sorted specification list. So this is just using the bound from above, knocking out the steps because of the corollary we saw, and replacing an inequality with an equality. Now for a more interesting example using effects. We have a simple algorithm that takes a random sublist of a list, keeping each element with 50% chance. And then if you keep the element, you incur 1 cost. You would hope to bound this by something like the binomial distribution, which is very similar to the sublist program. Here we take in a natural number, and then we compute an f of 1, which is really just a cost. And this is an implementation of a program for the binomial distribution. You'd hope to compare these programs and say that sublist is bounded by binomial, but they don't have the same type exactly. So we define an auxiliary function that will help us deal with these kinds of cases. So we have this result erasure, which just takes an f of a and gives you an f of 1 by deleting the a result. And this is useful when you only care about cost and not the behavior. So we can then say things like, well, the function that takes in a list and gives you its result erased sublist, in other words, just the cost incurred by sublist of L, is the binomial distribution on the length of L. And as a lemma, you might know that the binomial distribution on n is upper bounded by n cost, so you can give this upper bound as well. Now let me bring us back to list map from the very beginning. This is adjusted for call by push value now. As I mentioned before, if f is allowed to perform arbitrary effects, there's really no hope for doing anything good. It's possible that f could be flipping coins or messing with mutable state. The order in which the recursive calls happens could matter. This is, it's not really tenable to expect a good bound. So there are a few options. The first one is to just give up. you can give a trivial bound. But this does mean something. This is saying that map, if you don't make any other assumptions, costs what it costs. So when you're working in Decalf, you can use reflexivity to say, yeah, this program just costs itself. And if you want to understand how this works, read the code. However, if you have some simplifying assumptions, you can give better bounds. For example, if you know that the cost of f is always bounded by a constant c, then you know that calling map on f in a list is bounded by c times the length of the list cost. So this sounds more like the O of n bound you might be expecting for map. But in the presence of effects like randomization, you can also say more advanced things like if f is bounded by the binomial distribution on n cost, then map fl is bounded by the binomial distribution on n times length of l cost. So you can give these more advanced bounds. All right, so let me briefly talk about the semantics in my last couple minutes. So we give a topos theoretic semantics that's based on directed type theory a little bit. So it's also based on synthetic domain theory. So we're defining a path relation in the semantics, assuming that we have some interval object. And this is just saying that you have a map out of the interval such that the left endpoint is x and the right endpoint is y when you expect x to be less than or equal to y. And hopefully we would satisfy all those properties we saw earlier, but a priori this only is a reflexive and monotone inequality relation. So we have to do a little bit of work to make sure that this is transitive pointwise on functions and extensionally discrete. To make sure that it's extensionally discrete, we can just ask that the interval be extensionally trivial, because then any map out of the interval is going to be a constant, so the left and right endpoints will be the same, and therefore you have your equality. So that solves one problem. And to solve the other problem, to get transitivity and pointwise on functions comparison, then you realize that there's just a reflective subuniverse of types for which this does hold. So you can, instead of working in this larger category, just find yourself in the reflective subuniverse, and then you get the last two properties that you want. So for a non-trivial model, here is a summary of the axioms we need. We need an interval object I. We need a discrete type of natural numbers, a proposition x, and we need it to be the case that I is extensionally trivial. And the model that we have in the paper is augmented simplicial sets, which is like simplicial sets, but where you have an additional initial object, -1, in the simplex category. Then you get that the interval is the unate embedding of 1, and the extensional proposition is the unate embedding of -1. So now if we wanted a cost model like we had earlier with the natural numbers, we can define it as a directed QIT, where you have this type omega that has, for the natural numbers, 0 and successor constructors, but you have this directed condition such guaranteeing you that n is less than or equal to successor of n. And to make sure this is a valid cost model, you check that extensionally this is trivial. Cool. So now let me conclude. There is plenty of future work that this opens. This is really the start, not the end. This helps us understand how we can analyze algorithms in this synthetic way. And for example, we hope to analyze, do amortized analyses, building on some work that I did with co-induction. We hope to support data abstraction and cost signatures, and maybe even separate the cost proofs from the correctness proofs. We hope to study more effects and do a deeper dive into parallelism, and even consider non-algebraic effects, such as unbounded recursion. We also hope to consider probability more or advanced cases, such as doing expected or with high probability analyses. So to conclude, CAF started off by doing synthetic cost analysis mostly at these F types, the free algebras, and Decalf adds support for general effects and higher order programs. It lets you compare programs using inequality to get these inexact bounds, and it's harmonious with the extensional reasoning, so you can turn cost bounds into correctness theorems. And to justify this, we have a topos theoretic semantics in the topos of augmented simplicial sets, and we have practical examples embedded in our AGDA development. So with that, I think I'm just about out of time, and I'd love to take some questions.
Do we have some questions?
Hi, so I had a question about your semantics, your topos semantics. I'm aware that call by push value semantics often have a junction between two things for U and F.
Yep.
being added. In your semantics, have you identified what this adjunction would be?
Yes. Yeah, so the category of augmented simplicial sets is where the value types are living. And for talking about cost, we just use the writer monad on that category. And the category of algebras for the writer monad is the category of computation types. I think that's pretty standard with call by push value.
So there is a question from Discord.
Sure.
Could you get an infinity cost for upper bounds by making your cost QIT co-inductive somehow?
That's an awesome question that I would love
Thank
to
you.
think about more. I don't know.
Yeah, so did I understand this correctly that types, oh sorry, yeah, the cost does not appear in the types.
That's right, the cost does not.
Yeah, so is there a reason why you chose to do this? Like there are frameworks which actually embed cost within the types or grade them with the cost. So have you tried comparing or what is the reason for doing?
Sure. I think that, so maybe the intuition I can give is we're working in a dependent type theory, and we're here a cost bound is just another program. So rather than saying that you have a cost, rather than putting the cost in the type, we want to have the cost bound be just another program that you're comparing to that can have arbitrary effects involved, which could be cost, but it also could involve randomization, for example, like with the distribution example. I think this is more general, although I would have to think a little bit more before saying that definitively. Thanks.
I was kind of curious about your inequality. It's kind of an equivalent of the propositional inequality, which usually has some sort of transport operation. Do you have some eliminator for your preorder, or is it just there for the sake of counting things and there's no way really to eliminate it?
We don't have an eliminator at the moment. At least extensionally, you know it's equality, and then you can use the eliminator. But intentionally, I don't think we have an eliminator, and I don't think we ever would need it. I'm not sure.
I would expect it to be a bit more annoying because then you need to think about like covariant and contravariance of the predicate or something like this, which is one of the nightmare of directed stuff. So
yeah.
Okay, thank you.
I think we might have avoided that, luckily.
I have a question.
Sure.
Did you consider handlers of effects?
Handlers? Not at the moment. But it would be cool to figure this out.
Okay, any final questions? No? Okay, in that case, let's thank the speaker again.